Picture the solar system in motion. Most of the major planets spin like upright tops as they travel along their orbital paths. But the seventh planet operates differently. Uranus rolls along its orbit entirely on its side. This diagram illustrates axial tilt. Using the solar system's horizontal plane as a baseline, Earth's rotational axis is pitched at 23 degrees. But applied to Uranus, the axis drops to a staggering 98 degrees. Its poles align almost perfectly parallel with the orbital plane. Planets do not form this way naturally. For a celestial body of this mass to be resting completely on its side, the structural mechanics of the system must have been violently broken long ago. To account for this severe physical deformity, astrophysicists point to the giant impact theory, a specific kinetic event early in the solar system's formation. Around 4 billion years ago, a wandering protoplanet carrying roughly twice the mass of Earth collided laterally with Uranus. The angle and velocity of this collision were highly specific. The strike lacked the energy to shatter the gas and ice giant completely, but it transferred enough rotational momentum to permanently knock the entire planetary axis over. The immediate aftermath left a massive cloud of expelled debris. Over time, that primordial rock and dust coalesced into an expansive, dark gray ring system that now encircles the planet vertically. The remaining shrapnel from the impact spread further out, eventually accreting into a complex orbital network of 28 captured and formed moons. The severity of that early kinetic trauma left an enduring physical scar, locking Uranus into a sideways trajectory that continues to govern its behavior today. Astronomers classify Uranus as an ice giant. Unlike terrestrial rock planets or gas giants like Jupiter, the bulk of its mass is a hot, dense subsurface ocean filled with volatile chemicals, specifically water, ammonia, and methane. Almost everything known about this chemical makeup comes from a single historical encounter, NASA's Voyager 2 probe, which performed the only successful flyby in 1986. Data from that mission confirmed that the high concentration of methane gas in the upper atmosphere actively absorbs the red portion of the light spectrum. The sunlight that bounces back out creates the planet's distinct, nearly featureless cyan shell. This map tracks Uranus's 84-year orbit. Because of its 98-degree tilt, one pole is aimed directly at the sun, soaking up 42 years of continuous sunlight. Meanwhile, the opposite hemisphere is plunged into a 42-year winter of total darkness. The collision billions of years ago created a thermodynamic environment completely isolated from normal planetary behavior, resulting in the most imbalanced seasonal distribution of energy in our solar system. If you descend beneath those quiet, freezing upper clouds, the atmospheric pressure multiplies rapidly, reaching extremes that trigger violent chemical reactions. Deep in the mantle, the immense weight of the atmosphere crushes the methane molecules. The pressure actually forces the carbon atoms to separate from their hydrogen bonds and compress into solid crystals, a phenomenon astrophysicists refer to as diamond rain. Because these newly formed, dense diamonds are much heavier than the surrounding fluid, they sink rapidly like heavy hailstones, slowly drifting down through the water-ammonia ocean toward the rocky core. Far out of sight from any telescope, the interior of Uranus operates continuously as a vast, high-pressure chemical engine. Billions of years from now, the Sun will eventually exhaust its nuclear fuel, initiating the final stages of its life cycle. As the core destabilizes, our star will rapidly expand into its red giant phase. It will swell to hundreds of times its current size, entirely consuming the inner rocky planets like Mercury, Venus, and Earth. At nearly 2 billion miles away, Uranus is distant enough to survive the physical expansion. However, the expanding sun will subject the ice giant to a massive, sudden spike in solar radiation. This intense heat will trigger a temporary thermodynamic thaw across the system. The thick, icy shells of major moons like Ariel and Titania will melt, exposing dark, liquid subsurface oceans to the vacuum of space. Paradoxically, the highest temperatures this freezing system will ever experience will only occur during the chaotic death throes of its host star. This chart illustrates the star's final transition. After shutting its outer layers, all that remains of the Sun will be a dead, incredibly dense, and dim remnant core known as the white dwarf phase. With the Sun's nuclear furnace extinguished, the amount of thermal radiation reaching the distant Uranian system abruptly plummets to near zero. Any newly formed liquid oceans on the moons will rapidly freeze solid once more. Beneath the planet's cyan clouds, the dropping temperatures will permanently stall the deep atmospheric engine and halt the diamond rain. Stripped of its external heat source, Uranus is destined to spend eternity coasting through the dark as a pitch-black frozen relic, a fitting end for a permanently disrupted world.